안녕하십니까. 로데 슈바르즈 코리아의 최지홍입니다. 오늘도 여러분께 웨비나와 함께 돌아왔습니다. 오늘 참석해주신 여러분들 모두 대단히 감사드립니다. 네, 오늘 준비한 저희 웨비나는 고정밀 GNSS라고 하는 분야입니다. 제가 기억하기로는 최근이라고 표현할 수 있을까요? 요 근래에 들어가지고 또 작년에도 그 고정밀 GNSS에 관련된 웨비나를 했던 기억이 있어요. 그래서 아마 이 고정밀 GNSS라고 하는 부분이 또 새롭다고 할 수 있겠지만 또 한편으로는 이미 또 했던 내용들의 어떤 연장선상이 아닐까, 추가적인 어떤 내용들을 또 말씀드릴 수 있지 않을까, 이제 이런 생각을 하면서 또 준비를 했었습니다. 우리가 흔히 이제 차량에서 GPS라고 부르게 되는 그 내비게이션에 연관되는 이쪽에 해당되는 부분이 이제 GNSS라고 부르는 부분일 텐데, 오늘 이 고정밀 GNSS에 대한 내용으로 여러분께 또 재밌는 이야기들을 말씀드릴 수 있을 것 같아서 또 많은 기대를 가지고 준비를 했습니다. 오늘 웨비나를 진행하기 위해서 저희 기술지원팀의 김영서 매니저님 자리 함께 해주셨습니다. 김영서 매니저님 인사해 주시죠.
네, 안녕하십니까. 저는 로데 슈바르즈에서 신호 발생기, 분석기, 파워 센서 등 범용 장비군의 기술 지원을 담당하고 있습니다. 주요 제가 이제 담당하는 어플리케이션이 GNSS나 레이더 쪽 어플리케이션이다 보니까 오늘 이 자리에 함께 할 수 있게 되었습니다. 만나 뵙게 되어서 반갑습니다.
네. 오늘 저희 준비한 이 GNSS, GPS라고도 일반적으로 이제 GPS라고도 부른다라고 말씀을 드렸는데요. 김영서 매니저님, 그 GNSS, 특히 이 내용을 앞에 하이 프리시전이라고 해서 고정밀 네네. GNSS라고 이름을 붙였는데, 네네. 고정밀이라고 이야기를 해야 되는 어떤 특별한 이유가 있을까요? 일반적으로
GNSS라는 기술이 다양한 그 거리 오차를 줄인다고 해도 보통 5에서 한 10m 정도의 거리 오차를 가지고 있습니다. 근데 이 고정밀 GNSS라고 불리는 것들은 이 거리 오차를 최대 1m 이하까지도 줄일 수 있는 이런 기술을 고정밀 GNSS라고 보시면 될 것 같습니다.
그러면 우리가 현재 일반적으로 이 GPS라고 부르는 분야는 이 오차 범위가 최대 10m까지 갈 수 있는데 이걸 확 줄였기 때문에 고정밀이다, 이렇게
네,
표현한다는
네, 그렇게 생각하셔도 괜찮을 것 같습니다.
5m에서 10m면 대략 버스 한 대 정도 길이가 될 것 같은데요.
네네.
이 정도 오차라고 하면은
네네.
경우에 따라서는 내가 경부선 고속도로에서 상행선을 타고 가고 있는데 오차 때문에 하행선에 있는 것처럼 보여질 수도 있는 그 정도 오차가 되는 거 아닐까요?
아니, 실제 그런 내비게이션 기술 같은 경우에는 이 GPS 기술, 그러니까 GNSS 기술 플러스 그 내비게이션 맵의 소프트웨어 기술을 통해서 그거를 만들어주기 때문에 그런 일은 발생을 하지 않지만, 이 고정밀 GNSS 같은 경우는 후처리 소프트웨어 작업 없이 이 GNSS 기술만으로도 1m까지의 오차율을 만들어줄 수 있는 기술이라고 보시면 될 것 같습니다.
그러면 이게 내비게이션과 같은 어떤 어플리케이션 소프트웨어 도움 없이
또 GNSS 기술만으로도 1m까지의 오차율을 만들어주는 그런 기술이라고 보시면 될 것 같습니다.
네, 지금 자연스럽게 이야기가 나왔습니다만 오늘 제목 보시게 되면 하이 프리시전 GNS와 그 차량, 오토모티브 어플리케이션에 관련된 이야기로 저희가 준비가 되어 있습니다. 오늘 그 차량 쪽에서 특별히 이 고정밀 GNSS에 대해서 어떤 필요성이 제기되는 부분이 어떤 내용이 있을까요?
최근에 차량 관련 산업 같은 경우에는 가장 대두되고 있는 부분이 자율주행 차량입니다. 그래서 자율주행 차량으로 가기 위해서 지금 레벨 5 단계의 자율주행 차량을 가기 위해서 다양한 하이테크닉 기술이 포함이 되어 있는데요. 그 중에 레이더 기술도 있을 수 있고, 라이더 기술도 있을 수 있고, 다양한 V2X, 차량 간 통신 기술도 있을 수가 있는데, 그 중에서 자율주행 차량을 만들기 위한 테크닉 기술 중에 가장 빠질 수 없는 기술은 GNSS 기술입니다. 오늘 세미나를 들어보시면 아시겠지만 GNSS 기술이란 건 언제 어디서나 우리가 서비스를 받을 수 있는 기술이기 때문에 자율주행 차량에 반드시 필요로 한 기술이라고 보시면 될 것 같아요. 그러면 이제 자율주행 차량으로 가기 위해서는 굉장히 좋은 위치 정확도가 필요한데, 이때 고정밀 GNSS 기술이 이 테크닉을 완성시켜준다고 보시면 될 것 같습니다.
네, 지금 저희가 보는 화면에서는 지금 여러분께서 같이 보시고 계신 송출 화면도 보입니다만은 지금 채팅으로 올려주시는 이 글들도 저희가 함께 보고 있어요. 그런데 지금 이형준님께서 이제 아까 저희 얘기했던 부분을 이제 바로 그 코멘트를 달아주셨는데요. 예, 맞습니다. 이게 지금 좀 전에 설명드린 것처럼 신호의 문제라고 표현한다기보다 한계라고 이야기하는 게 좀 더 맞을 것 같아요. 이 GNSS에서 이 위치를 파악할 때 발생할 수 있는 어쩔 수 없이 포함될 수 있는 이런 오류에 대한 부분을 이야기하는 거고, 아까도 그래서 설명드린 것처럼 사실 내비게이션 후처리 소프트웨어에서 이제 이런 부분들을 굉장히 많이 보완을 하고 있다. 이렇게 해석을 할 수는 있을 것 같습니다. 이게 아까 또 말씀드렸던 내용에 이제 포함이 되었던 부분일 것 같고요. 오늘 저희 준비한 내용은 아까 시작 부분에서 아마 보셨겠습니다만은 강사가 세 분이에요. 지금 저희 오늘 준비한 내용은 저희 로데 슈바르즈 본사에서 글로벌로 진행했던 웨비나 내용을 저희가 가지고 온 거고요. 그래서 지금 GMV라고 하는 회사에서 오신 게스트가 또 한 분이 포함되어서 총 세 분의 연사가 아마 화면에서 보이게 될 겁니다. 그래서 실제로 이 고정밀 GNSS 기법들을 실제 어떤 식으로 어플리케이션 적용을 했느냐, 이제 이런 어떤 실례라고 생각할 수 있을 것 같고요. 이런 면에서 내용들을 보시게 되면 아마 좀 더 어떻게 표현해야 될까요? 프랙티컬하다고 표현해야 될까요? 좀 더 실제적인 어떤 그런 예를 좀 보시는 면도 되지 않을까, 이런 생각이 들어서 내용을 또 저희가 준비한 부분도 있을 것 같습니다. 이제 저희 내용들을 쭉 보시면서 또 이 GNSS 기술이 어떻게 발전해서 어떤 식으로 에러를 보정해서 좀 전에 말씀드린 것처럼 신호 자체에서 한 5m에서 최대 10m까지 포함될 수 있는 이 오류에 대한 부분들, 측위 오류에 대한 부분들을 어떻게 극복을 하고 있는 거냐, 또 어떻게 더 이거를 정밀하게 만들고 있는 거냐, 이런 부분들을 함께 보시는 내용이 될 것 같고요. 그리고 동영상 자체는 지금 이 웨비나 내용에서 마지막 부분에서 이제 실제 측정에 대한 부분들을 어떻게 해야 될 거냐, 이런 부분들에 대한 개략적인 부분도 포함이 되기 때문에 실제 여러분들께서 이제 개발을 하시고 내용들을 시험하실 때, 어플리케이션을 실제 시험을 하시면서 측정을 하신다는 면에서 볼 때에도 어떤 내용들을 좀 함께 고민해 볼 수 있는 그런 내용들이 아닐까라고 생각을 합니다. 그래서 지금부터는 실제 저희가 준비한 글로벌 웨비나 내용들을 함께 보시면서 내용 쭉 들으시고요. 뭐 항상 그래 왔었습니다만은 계속 질문들 필요하신 부분들은 계속 올려주시면 저희가 이 동영상 마무리 끝나고 나서 이 Q&A 시간을 통해 가지고 내용들을 또 답변을 드리고 그렇게 진행을 하도록 하겠습니다. 지금부터는 웨비나 동영상들을 함께 보시도록 하겠습니다.
Welcome to our webinar on how High Precision GNSS enables new automotive applications. My name is Colin Mulligan, and I'm the Market Segment Manager for Automotive Connectivity working at Rohde Schwarz. Today, I'll be joined by Marcus, our expert from GNSS, and a special guest, Jose Luis from GMV. Our agenda today will talk through how High Precision GNSS enables emerging applications, some basic principles of High Precision GNSS, how a High Precision GNSS network works, testing of High Precision GNSS, and some summaries and conclusions. But first, I'd like to give a quick overview to the GNSS technology. There are 6 major constellations in the globe, 4 of those with global coverage. And as we can see from the graph on the right-hand side, in the last number of years, we have a large increase in the number of satellites deployed. There are well over 100 deployed satellites, and positional accuracy from these satellites can vary greatly, and that's why we need High Precision GNSS, and it helps to improve this even further. A vehicle has many sensors in the car, and as you can see from the slide, we have radar, camera, inertial measurement units, V2X, LiDAR, ultrasound, cellular, high-definition maps. However, GNSS is the only sensor which provides an absolute position today. So, High Precision GNSS, what are its characteristics? So if we look at the slide, we can see on the outside, we have about a 10-meter range for accuracy. And this improves as we go through applying different technologies. Firstly, High Precision GNSS will help us to get an accuracy of less than 1 meter, typically 10 centimeters. It provides a global footprint. The automotive industry does not want country-specific solutions. It has a high degree of integrity for the positional accuracy. And finally, a continuity of service. You need a service for 24 hours a day, 7 days a week. So what are these key automotive applications? Well, today, we all know about using map navigation and emergency call. But in the future, High Precision GNSS will enable autonomous driving and cellular V2X applications. Emerging applications require High Precision GNSS. So what I'd like to do now is I'd like to hand over to my colleague Marcus Issigler, who's going to provide us with some basic principles. Marcus, over to you.
Thank you, Colm, and welcome also from my side. In the next few minutes, I will talk a little bit about the basics of High Precision GNSS. We will see how it works, how GNSS observations are processed, how typical GNSS errors can be minimized, and also how the infrastructure for typical High Precision GNSS services look like. But before going into the details, let's just start off with an overview on different positioning methods and the positioning accuracies that can be achieved when using these methods. When discussing positioning accuracies, it's very important to note that it is only possible to provide rough rule of thumb values. And the reason for that is that actual accuracies depend on many different parameters, like how many satellites are being used in the position solution, how are these satellites distributed across the sky, also what are the signal reception conditions, and also what signals from what frequency band are being used. But as a rule of thumb, and this is what you can see here in the slide, with standalone single frequency GNSS, you can achieve position accuracies between 5 and 10 meters. This can be significantly reduced to about 3 to 5 meters when using dual or even triple frequency GNSS. And even further enhancements can then be achieved in a next step using differential techniques based on range or error corrections. And this can lead to position accuracies down to 1 meter. But when accuracies of less than 1 meters are needed, then we need to go from code to carrier processing and also use differential techniques or more sophisticated error modeling approaches. This is called High Precision GNSS. So where are these different positioning methods typically used? Code-based range corrections or error modeling approaches are typically used in the augmentation systems like S-Bus and G-Bus, and the corresponding carrier-based processing techniques are really used in high-precision GNSS services like RTK, PPP, and PPP-RTK, which we will discuss in more detail in a minute. But before we dive deeper into these high-precision GNSS topics, let's first talk about where the limited positioning accuracy of single-frequency GNSS comes from, and then about how more and more errors can be mitigated when we go step by step to the more sophisticated positioning methods. So the basic measurement in GNSS is the distance or range between a satellite and a receiver. And this is what a GNSS receiver measures, and this measure is called pseudorange. Why is it called pseudorange? Because it does not represent the true distance between the receiver and the satellite, and the reason for this is that this pseudorange contains typical errors, and these typical errors are listed here on the slide. The first error is, or the first source of error is the atmosphere. So when the signal propagates through the different layers of the ionosphere and also the troposphere, it gets delayed and attenuated. Then we have satellite orbit errors here, which is basically the difference between the actual satellite orbit and its predicted orbit, which is usually used for the positioning process. Then we have clock errors on the satellite and clock errors on the receiver side. This is basically the difference between the local time on the satellite and in the receiver and the GNSS system time. And finally, we also have measurement noise and multipath, and the latter is caused by signal reflections in the vicinity of the receiver. So we are talking about reflections coming from buildings, from trees, or from the ground. And all these error sources limit the typical positioning error to about 3 to 10 meters, if we like we have seen in the first slide. So here on this slide, you can see exactly where these 3 to 10 meters come from. So this list here shows the typical values for the different errors under relatively normal conditions. And as you can see here, they add up to, in this case, to a ranging or user equivalent ranging error, UERE, of about 7 meters. The atmospheric errors can then be reduced in a first step by applying atmospheric models directly in the receiver, which in our case here reduces the total ranging error to about 3 meters. We can then compute the expected horizontal positioning accuracy, and this can be estimated by multiplying this ranging error, these 3 meters, with the so-called horizontal dilution of precision, HDOP. So what is a DOP value? Well, this is simply a measure how well the satellites are distributed in the sky. And the satellites can be evenly distributed across the sky, more or less, like we see here in this example. Or in some cases, the satellites tend to concentrate in certain parts of the sky. In such a case, the geometry becomes worse and the DOP value increases. Here in our case, we just assume, let's say, average geometric conditions. Some satellites are obstructed from view, so we calculate with a DOP value of 2.5 here in this case. And this results in a positioning error of about 8 meters. And this is well in this 3 to 10 meters range that we have postulated before for standalone single frequency GNSS positioning. And although this is not too bad, we of course want to get rid of these error sources as much as possible. And if we want to get really in the sub-meter position accuracy range, we need to further reduce or even eliminate as many of these error sources as possible. And one first step is to deal with the potentially largest error in this list, which is clearly the ionospheric delay. And this can be done using dual or even triple frequency measurements. So let's start here with a closer look at how the ionospheric delay can be modeled. We can take a look at this formula, and we can see that the ionospheric delay for GNSS signals depends on the total electron content in the ionospheric layers right above the users. This is this TEC parameter here. It also depends on the signal's carrier frequency and on the signal elevation. And this results in typical path delays that are displayed here, down here in this diagram. They have been computed for, let's say, normal ionospheric conditions, so no solar storms or similar events. They have been computed for the GNSS frequencies L1, represented by the blue bars, and also L5, represented by the red bars here, and for different elevation angles. And as you can see, they range between 2 and 15 meters. As I already mentioned before, these delays can be reduced even by a single frequency GNSS receiver by about 50% with the help of dedicated global ionospheric models. And one example of such a model is the well-known Klobuchar model for GPS, whose parameters are transmitted in the navigation message of the GPS signal, so that the receiver is able to decode these parameters and is also able then, based on these parameters, to estimate at least roughly the ionospheric delay. But in order to completely remove the error, the receiver can use range measurements obtained from 2 frequency and either form a completely new observable, the so-called ionosphere-free pseudo-range that you can see here, or compute a range correction and apply it to the range measurements taken on 1 frequency. Both approaches are really able to almost completely remove the ionospheric delays, but certainly all other errors like the tropospheric error, the orbit error, the clock error, also noise and multipath are certainly still there. So in order to learn how these remaining error sources can now be mitigated, we will now look at the basic principle of local area differential GNSS positioning based on code observations. This positioning approach works with a GNSS reference station located at a well-known position. And this reference station is now able to compute the range to the satellite in two different ways. So first, it can do a normal receiver measurement, which is indicated by the blue arrow here. This measurement certainly contains all the typical error sources we just discussed. Or it can do a computation of the expected real range to the satellite based on the known coordinates of the reference station and the known coordinates for the satellite. So the satellite position is something which is known basically because it is transmitted in the form of orbit parameters in the navigation message. And this calculation is indicated by the red arrow here. And the difference between the blue and the red arrow contains all the ranging errors and can be transferred to the user in the form of a correction. And the user can then combine this transmitted range corrections with its own range observations taken directly from the user receiver and is thus able to get a more accurate range measurements, which in the end will also lead to a more accurate position. So this type of correction is called observation state representation, OSR. Why? Because the transmitted correction data is derived directly from the reference receiver's observation. Just a few words on error mitigation. So what errors can be mitigated? You see this here in this table. The answer is all errors that are common or very similar for both the reference station and the user can be eliminated or at least reduced to a large extent. It should also be noted that the resulting positioning accuracy in the end depends on the distance between the reference station and the user. The accuracy is generally better for short baselines because the errors are better correlated in this case. So whenever we have a rather small service area with relatively short baselines, this method can be used to mitigate most error sources. And this method basically works with only one single reference station. And as we have already seen, the correction data is based on range corrections, and therefore the correction type is OSR in this case. And here's an implementation example for such a system, which is the ground-based augmentation system. This system provides differential corrections to incoming aircraft to support landing procedures at airports. So what if the service area needs to be larger or to get larger? In this case, we cannot work with a single reference station, but we need a network of reference stations. And the observation from all these reference stations are then processed in a central processing facilities where the pseudo-range errors are split into its constituents and provided to the users inside the service area. And this correction type is usually called space state representation SSR. And this approach is typically used in satellite-based augmentation systems like WAAS, EGNOS, EMSAS, or GAGAN. So as we have already seen, these code-based augmented positioning methods, they can achieve positioning accuracies of down to 1 meter. But when sub-meter accuracy must be achieved, it is mandatory to use carrier observations instead of code observations. The typical measurement errors that we have discussed, they will still be there, but they can be mitigated by double differencing carrier observations. So let's have a closer look at this concept. So we still have our two receivers here, so the reference receiver and the user receiver here. And now we can take observations from these two receivers at the same point in time to the same satellite and subtract them from each other. This is called a single difference. And by doing this, these errors here, indicated in green can all be eliminated or reduced. So satellite clock errors, satellite orbit errors, and the atmospheric delays can be reduced. And we can even eliminate the receiver clock error, which is still present for the single differences, by simply take another satellite, compute a second single difference with another satellite. This is the one illustrated in red here, and difference both single difference, and this is called a double difference. And the only errors left in this case are noise and multipath. So this is still present. Why? Because these are the errors that are not spatially correlated and they cannot be differenced out. So using double differences is certainly only a first step to compute the highly accurate user position. Other steps include also rather complex concepts like carrier ambiguity resolution or baseline processing. And these processes can also result in rather long convergence time, which is simply the time the receiver needs to compute the first highly accurate position. If we have a look at the system characteristics here, also in this case we can distinguish between small service area where only one reference station is sufficient and larger service areas where we need a network of reference stations. So also in this case it is required to send correction data to the user. What is being sent? It's in this case simply the carrier observations taken at the reference stations. So the correction type is also always R here. And this kind of implementation where really carrier phase observations are directly sent from a reference station to a GNSS user, and the user then uses this observation to compute a highly accurate position is called real-time kinematic RTK. So RTK itself, it's not really new. It has been around for many decades, but mainly for surveying applications. But RTK is now finding its way into many other applications as well. Again, in case the service area needs to be larger, so the situation on the right-hand side here, a network of reference station is used, and also observations from all the reference stations are processed in a central processing facility where typically precise orbit and clock parameters and corrections are generated and then provided to the user. So we are also talking about SSR in this case, and this implementation method is called precise point positioning and is widely used by commercial high precision service providers. And one of the reasons why it is so widely used is because PPP has some major benefits over the RTK approach, as we will see later in this webinar. Now let's have a closer look at the infrastructure for RTK and PPP systems. Let's start with RTK. We have here on the left-hand side the typical RTK infrastructure with a GNSS constellation, a reference station, and a GNSS user. So what happens when using this positioning method is the following. First, the reference station collects carrier phase observations. Then these carrier phase observations are sent from the base station to the user, hence the OSR correction type. And then the user receiver collects also carrier phase observations by itself. And as a final step, the user receiver combines its own observations with those received from the reference station and is then able to compute a highly accurate position. And this position computation is based on what we have previously discussed, double differencing, ambiguity resolution, and also baseline processing. The situation for a pure PPP service is slightly different, and this is what you can see on the right-hand side of the slide. The infrastructure again includes the GNSS constellation, a network of reference station, and again a central processing facility. Plus, in this case, additional infrastructure is needed to really send correction data to the user. This can be done by using, for example, a satellite link, in this case a geostationary satellite, or also terrestrial communication links like internet or a cellular network. Now let's have also a closer look what happens during positioning. So the base station network collects pseudorange and carrier phase measurements and observations. They are transferred to the central processing facility where satellite, orbit, and also the clock corrections are computed. Then these error corrections are transmitted to the user, for example, via geostationary satellite or internet or a cellular connection. And then on the user side, the user receiver can apply these error corrections to its own GNSS measurements and compute a highly accurate position. In terms of error mitigation capabilities, RTK can mitigate really all major GNSS error sources, which is mainly due to the basic principle of forming these double differences that we discussed before. On the other hand, a pure PPP service can only mitigate the satellite clock and orbit errors. And this is why in the meantime, many PPP service providers also provide correction data for atmospheric errors. And this service is then called PPP RTK. And this provides better position accuracy than a pure PPP service. So speaking about position accuracy, and here I already come to my final slide, which is a summary of all the positioning methods we have discussed so far. So we have a standalone GNSS here, we have augmented GNSSs here, and High Precision GNSS. All methods are listed here together with their correction types, so OSR versus SSR, with their observable type, code versus carrier, the service area, so local, regional, or global, and also their capability to mitigate the typical GNSS errors, and of course, with their resulting position accuracy down there. So the main takeaways of this slide are, in case sub-meter positioning accuracy is needed, really carrier-based positioning methods are mandatory. And if we have a closer look at these positioning methods, these high-precision GNSS methods, we see that PPP services provide accuracies of several decimeters. With PPP RTK services, you can get better than 10 centimeters, and RTK is able to provide the best accuracies in the centimeter range, but only in case you are relatively close to a reference station. And this is also the major disadvantage of such RTK systems, because in case you really want to cover a very, very large service area, you need a lot of reference stations. And this makes such a system very expensive and sometimes uneconomic for the service provider. As you can see here from this slide, a very good trade-off between accuracy and the infrastructure complexity is therefore PPP RTK, because it combines really high positioning accuracies with a potential global coverage. And this is really why many high precision GNSS services are today based on PPP RTK. So this already concludes my part of the webinar, and I give back to Colm.
Thank you, Marcus. That was very, very interesting.
Thanks.
Okay, and with that, I'd like to introduce our next guest. And Jose Luis is from GMV, and he's going to talk a little bit about how high precision GNSS networks work. Jose Luis, over to you.
Thank you very much, Colm, for having us here at GMV. So, as you mentioned, I'm going to explain how our solution of GNSS technology works for autonomous driving systems. So, this would be a summary of what you have already said. I'm going to explain here how our specific system works, applying all the theory that our colleague Marcus has been explaining so far. Here I would like to point out that the GNSS is one of the only ones in the autonomous driving cars that is providing global coverage. This means that the system is providing a high accuracy and safe solution everywhere, all around the globe. And actually, another main topic of this solution would be that it's very robust in terms of safety, because we have been working in this system for quite a long time, and it's really a mature system that has reached and demonstrated that this SOTIF, like in many applications for civil aviation, that now is a key enabler for also transitioning into the road-based vehicles. An important part of this system is that it's independent from the rest of the system integrated in the cars. And that gives us a lot of advantages, because whenever the others are not available, GNSS is going to be there, and it actually can be enhanced by merging this system with others in the cars, like the inertial measurements or the odometer, for example. We provide also a velocity and orientation values, which are really also useful for the different other systems in the car that are using our output. An important part of the system is that there is no specific setup that is only used for GNSS high accuracy. This setup can be also used for many other applications, such as e-call, the tolling, tachograph, or navigation, as our colleague has explained before. There is another important part of the system, and it consists of the anti-spoofing and anti-jamming detection capabilities, which is very important in order to avoid this kind of attacks that potential hackers could do to our system. So we want to make sure that the car is every time in the location that we are saying it is. So it's very important to have this kind of checks inside the system. And why GNSS? Why do we use GNSS in the autonomous driving system? Because this is a system that has been booming in the past few years. As you can see, because all the different governments have been spending a lot of time in order to develop their own GNSS, a global navigation system, basically. And we see that this has a lot of potential, and that a lot of industries are using this kind of technology. So now I'm going to focus on our specific product, which is called the GMBG SARP. This stands for Safe and High Accuracy Reliable Positioning for Automotive. Let me tell you that we have recently won this award from CLEPA, which is an organization that gathers all the different suppliers in the automotive industry. So this has been recognition to all the effort that we have put into the innovation process of our product. So we are very proud to show it here. What does it consist of? So basically it has two different wings. The system we have been developing has in the first part the correction service, and the second part of the positioning engine that I will explain in the next slides. So the first part of our system is basically the correction service. Why do we need a correction service? As our colleague Marcus was explaining, this is the service that is basically computing the exact and accurate position of the satellites with a high accuracy, also the clocks, and all these kind of different errors that can be mitigated in this ranging that he was explaining before. So the important part is that all these corrections are sent through this delivery chain into the car, where the second part of the system, which is the positioning engine, is running and making use of these kind of corrections on top of the observations that we receive from the satellites that we have in view in that moment. So an important part of the system is that it has been developed under all these kind of standardization and processes that make it really reliable in terms of safety, in all the safety aspect, and cybersecurity, risk management, among others, basically. So I'm going to talk here about the correction service, which is the first part of our system. And this is mainly consisting of this infrastructure that you can see here. The first part would be the global GNSS network. which is owned by GMB, and actually is the one in charge of computing all these orbit and clock corrections and the carrier phase biases and so on. And then we have the regional GNSS network, which is the one in charge of computing these ionospheric corrections that Marcus was explaining before. So all this data is mainly used in order to provide a fast convergence, high accuracy, and safe positioning to the users. So this information goes throughout our processing servers, which are the ones in charge of computing these kind of corrections. And this is basically deployed in two different fast convergence areas by now, which is Europe and North America region. So these servers are basically consisting on the correction processor, and then we have the safety processor as well, in charge of sending all the different kind of information about the different satellites and the different corrections that we are computing, telling the user use this satellite or do not use these satellites, or this kind of information. So all this is sent, as I was mentioning before, throughout the delivery chain, which is a service 24/7 to the user, because of course, any user all around the world wants to use its own car at any time, and you cannot stop the service that you are using. So this is why the requirements related to the service availability are so stringent, which we have a 99.5% of availability. And also in terms of accuracy of both the orbits and the clocks, basically. There is also something in which we have been working on, which is called the Global Ionosphere Model. And it's one approach that is going to be followed in the next years, because it's going to reduce the complexity and the costs of this regional network computing, the ionospheric model. So we hope that this, in the near future, you will see the results and its potential usage. And as I was saying before, this has been also designed and developed following all the rules specified in the different ISOs. So what about the second part that I was mentioning before, which is the one embedded in the car, and it's called the positioning engine. So this one, as our colleague Marcus was saying, we have very stringent requirements, because obviously you want to know all the time where the car is located, and you need to know if it is in the right lane, and you cannot move out of such lanes. So as you can see here, the typical requirements that we work with are about 10 centimeters of horizontal accuracy. Also, the heading accuracies that we are working with are below 0.25 degrees. Both of these ones are 95. Also, we have this convergence time, which is has to be below 30 seconds. And also, whenever we have different GNSS outages, short as in the brief channels and the panels in the highway and so on, we have different quick convergence methodologies, which allows us to converge mostly instantaneously. Also, another very important part of this system is that within the positioning engine, it has a specific layer called the safety layer, which is the one in charge of providing to the user a certain protection level. What is this protection level? This is a measure that we give to the user so that he knows that the error that we are specifying whenever we provide the position is always overbounded by this protection level with a high probability. And this high probability is the number that we have here, which is 10 to the minus 7 per hour as a target integrity risk. And also we have horizontal velocity accuracies under 0.1 meters per second. So, as my colleague was mentioning before, the high achievement of this system is that it's able to obtain these values with a mass market automotive GNSS receiver. And why is this important? Because this can massively be used all over the world, and with a relatively cheap setup. So you can be wondering, how do we do this? I mean, how do we make sure that the values that we are obtaining and that these numbers that we are committing to are actually achieved? Well, the answer is by testing and validating the system. The test and validation activities can mainly be reduced to three different pillars, which are the software validation, the system validation, and the safety validation that I will explain in the next slide. And as our colleague Marcus was saying, this system that we are developing and integrating in the different cars is using the PPP plus RTK technique and also following all the ISO rules. So, as I was mentioning before, related to all the testing and validation activities, GMB has thoroughly tested the PE solution embedded in the cars across several driving campaigns accomplished in the last couple of years. So, if we focus first on the system validation, we have collected tens of thousands of kilometers all around Europe and North America, because we need to make sure that the system is behaving as expected. So how do we do that? So what we do is test the system and the different influence factors. As you can see here, how does the positioning engine behave when we are driving in mountains, when we are driving in high latitude surroundings? How does it behave with different environmental conditions in forest that we are covering the antenna and therefore we are losing many satellites? How do we behave in different tunnels that we are completely losing all the GNSS signals that we could receive? Well, we have done that in the last couple of years, as I was explaining before. And as you can see in the map, we have gone also through coastal areas. We have gone to Scandinavia in order to test the different scintillations of the ionosphere layer and so on. So on top of this system validation, we have the safety validation, because you can drive a lot of kilometers all around the globe, but at the end, there are always certain kind of errors that you cannot model. Because what happens if, for example, we drive north to the Scandinavian countries, and in the days that we drove there are no ionospheric activities happening, so we lost the chance to test it in real conditions. So what we have to do here is to include a massive faulty testing in order to insert different kind of errors in the GNSS measurements. So for that, what we need is a GNSS RF signal simulator that allows us to being able to include in these GNSS measurements the kind of error that we would expect to see in real life whenever we drive to the Scandinavian countries, for example, in order to test the ionospheric activities. What we achieve with that is, at the end, a lot of trust in our system that the protection levels that I was explaining before are always covering the error that we are computing whenever we are calculating the high accuracy position. So for this, as I was explaining before, we need to achieve this 10 to the minus 7 per hour integrity risk, and this is only achieved by this simulation on the errors that we include in the GNSS measurements. So that was the last part of my presentation, and we go back to Cole.
Jose Luis, thank you very much. And that was really, really interesting. I can see there's a lot of hard work gone into achieving that. I'm sure it'll help us on the way to autonomous driving vehicles in the coming years. Thank you.
Thank you.
So with that, I'd like to give people a little bit of an overview of some of the testing considerations around high precision GNSS. So if we firstly maybe start by summarizing what we've just seen from Marcus and Jose Luis. We have, on the left-hand side of this picture, we have a network of high precision GNSS systems. In the center of this system, we have a high precision correction server. And there are three basic mechanisms in which this information is brought to the car. One via satellites, two via an internet connection or a 5G LTE internet connection, and thirdly via a 5G system broadcast via POSSIBs, where we can address many vehicles at one time. So looking into high precision testing considerations, there are maybe 5 points which I would like to bring to your attention here. The first of those points today is we need to be able to test a GNSS receiver in a reproducible and controllable environment. Secondly, we need, as Jose Luis was mentioning, we need the ability to be able to inject errors into the system. So for example, ionospheric errors might not be in a location on a certain day. If you can, and your testing maybe is not so efficient, if you can inject those errors in a controllable manner into the system, you can do things much more efficiently. We also have the ability that we need to be able to test as a black box or as a system. So for example, a full vehicle in an automotive chamber. We want to be able to inject these errors and into the system. The fourth point is the possibility sometimes to test with the correction data from a live network with a live GNSS. We need to be able to do. And we need to be able to reduce the amount of time and resources spent on testing this. And these are maybe 5 points that I think are very important. So what I'd like to do now is I'd like to give you an overview of some of the different testing applications for high precision GNSS. So as we look at the slide, on the left-hand side, we see a signal generator generating high precision correction data. And this is typically what you do if you're doing GNSS receiver testing or modules in a lab. And a tier 1, a tier 2, or a silicon vendor might be very interested in that type of testing. The second type of testing is when we have an ECU or a TCU, a telematics control unit, and or a full vehicle, where you want to simulate the GNSS system, but also the delivery of the data over the 5G network. The third type of test system where you might want to do is, again, in the OEM context or tier 1 context, where you're taking the satellite feed into a chamber or a hall, and you want to do a functional smoke test to see if everything is working before you release the software. And so there's different configurations you can use to connect these up to save time and provide more efficient, reproducible testing. So finally, I'd like to give you a quick summary and conclusion of 3 things we've learned today. So the first topic, which I'd like to bring up, would be high precision GNSS positions based on RTK P2P can achieve the requirements for the automotive industry. The second point, there are 4 key pillars: high precision, global availability, integrity, and continuity of service. And the third point is testing in a controlled and reproducible environment is important to accelerate the development and testing of high precision GNSS. So with that, I'd like to conclude the webinar and thank Marcus and Jose Luis for their contributions. And I hope you found this interesting and look forward to further discussions with you in the future. Thank you very much.
네, 지금까지 저희가 준비한 영상으로 내용을 함께 하셨습니다. 말씀드렸던 것처럼 저희 본사에서 글로벌로 진행했던 웨비나를 저희가 자막을 추가해서 지금 여러분께 그 내용을 함께 보여드린 거고요. 아마 꽤 재미있는 내용들이 많이 있었던 것 같습니다. 김영서 매니저님, 그 오늘 진행됐던 내용 간단하게 아주 그 서머리 잠깐 부탁을 드려도 될까요?
그 오늘 진행한 세미나에 대해서 정리를 한번 해보면요. 우선 그 자율주행 차량에 그 고정밀 GNSS 기술이 어떻게 적용되는지를 설명하기 위해서 이 GNSS 기술에 대해 설명을 드렸고요. 각 GNSS 기술별로 그 고정밀 기술이 될 때까지 이 오차율을 줄이는 다양한 방식의 기술에 대해서 설명을 드렸습니다. 뭐 예를 들어서 뭐 듀얼 밴드의 그 채널을 써서 오차를 줄이는 방법, 아니면은 뭐 DGPS나 S바스를 이용해서 오차를 줄이는 방법, 최종적으로 고정밀 GNS를 쓰기 위해서 RTK나 뭐 PPP, 아니면 최근에 가장 많이 이용하고 있는 PPP RTK를 어떻게 사용하는지에 대해서 기술에 대해서 소개했던 시간이라고 보시면 될 것 같습니다.
예, 그래서 지금 오늘 크게 나누면 그 고정밀 GNSS에 대한 어떤 이론적인 배경, 그리고
네.
실제 GMV사의 어플리케이션을 통해서 이제 실제로 어떻게 적용이 되는지, 그리고 이런 경우에 이제 어떤 식으로 어떤 시험 솔루션들이
테스트를 어떻게 하는지,
예, 테스트를
예.
어떻게 하는지 그 중요성, 그리고 이제 마지막으로 전체적인 마무리 뭐 이런 정도로 진행이 됐던 것 같은데요. 제가 재미있게 봤던 부분은 이제 보통 이 GNSS라고 하면은 이거 위성에서 직접
네네.
내려오는 거기 때문에 그 흔히 통신에 대한 부분을 생각하지 않게 되는데, 지금 오늘 내용에서는 어떤 통신에 대한 부분이 같이 접목이 돼서
네네.
정밀도를 높여주는 이런 개념들이 좀 들어갔던 것 같아요. 이 부분에 대해서도 조금 더 설명을 좀 해주실 수 있을까요?
네, 뭐 정확하게 말씀하셨는데요. 그 기존의 GNSS 테스팅 같은 경우에는 GNSS 시뮬레이터만 있었으면 가능했어요. 근데 고정밀 이런 GNSS 솔루션 같은 경우에는 그 오차에 대한 보정 같은 경우를 뭐 인터넷망이라든지 아니면 위성통신, 그 추가적인 위성에 의한 통신에 의한 보정이라든지 아니면 사업자망, 그 다음에 뭐 그 브로드캐스팅망 이런 그런 환경을 통해서 보정 오차를 이제 받기 때문에 추가적으로 이런 테스트를 하기 위해서는 인터넷망이라든지 사업자망이라든지 위성통신망을 만들어줄 수 있는 추가적인 장비가 필요합니다. 그래서 우리 회사 같은 그 RNS 같은 경우에도 GNSS 시뮬레이터 플러스 이런 환경망을 만들어줄 수 있는 추가 장비를 연동을 해서 테스트를 하고 있는 추세라고 보시면 될 것 같습니다.
그 망을 연동한다는 이야기는 이제 네트워크를 시뮬레이터 할 수 있는,
맞습니다.
예, 통신 특정 솔루션에 대한 접목도 지금 활발하게 또 검토가 되고 있다, 사용되고 있다, 이렇게 볼 수 있다는
네,
얘기네요.
맞습니다.
예, 뭐 보통 컨버전스라고 이야기를 하기 때문에 이 기술이 발달하면서 옛날에 생각했을 때는 어떤 하나의 기술로만, 하나의 어떤 솔루션으로만 존재했던 내용들이 다른 어떤 기술들도 더 갖다 붙이면서 더 정밀해지고 더 어떤 활용성이 높아지는 이런 모양들을 실제로 우리가 보게 되는 그런 부분들이 아닐까 하고 생각이 됩니다. 네, 여기까지가 일단 저희가 준비한 내용들이었었고요. 질문들을 좀 보겠습니다. 그래서 오늘도 지금 굉장히 많은 분들께서 이제 질문들을 쭉 올려주셨어요. 그래서 뭐 저희 입장에서 참 흥미로운 내용들을 말씀해 주신 부분들도 있고 그래요. 우선 뭐 제 쪽에서 재미라고 표현하면 좀 이상할 수 있겠네요. 굉장히 흥미로웠던 어떤 질문은 여기 박일규님께서 올려주신 내용입니다. 그래서 그 내용으로 치면 어떤 군사용이라든지 어떤 산업 그 전략물자 수출 이런 부분의 어떤 연관성을 물어봐 주셨는데요. 예, 맞습니다. 저희가 고정밀 GNSS를 개발하시고 어떤 시험하실 수 있는 시험 측정 솔루션을 저희가 공급하는 게 맞고요. 다만 이 수출 제한이라고 하는 부분, 이건 뭐 오늘 주제는 아닙니다만은 이건 결국 파이널 프로덕트에 대한 내용으로 검토를 하는 부분이지, 어떤 파이널 프로덕트, 이 최종 제품을, 이거 소프트웨어나 하드웨어냐 뭐가 됐던 간에 이 최종 제품을 어떤 식으로 개발했냐, 무엇을 가지고 개발했냐, 요걸 따지고 얘기를 하는 건 아니기 때문에 아마 이 부분은 그 고민하시는 혹은 고려하시는 이 최종 제품이 어떤 부분을 어떻게 적용하고 있는 거냐, 어떤 부분을 어떻게 해결하는 부분이냐, 이런 어떤 사용처에 관련된 내용으로 좀 분리해서 생각하셔야 되는 부분이 아닐까라고 생각을 합니다. 그래서 저희 제품을 사용했기 때문에 어떤 수출 제한이나 전략물자에 걸린다, 이런 개념은 아니다. 이런 부분을 좀 저는 말씀을 드릴 수 있을 것 같고요. 네, 그리고 또 제가 또 흥미롭게 생각했던 부분은 이 부분이 내비나 플박의 실내나 음영 지역을 말씀해 주신 케이스가 될 것 같습니다. 그런데 요 부분이 아마 오늘 내용에도 잠깐 나왔었고, 좀 전에 이제 저희 이야기할 때도 잠깐 나왔던 부분이긴 한데요. 결국은 이제 이런 부분들을 보완할 수 있는, 왜냐하면 위성을 그렇다고 해서 지하 주차장을 끌고 내려올 수는 없기 때문에 이런 부분에서 이제 그런 보완할 수 있는 뭔가가 있어야 되지 않겠냐, 이런 이야기를 하게 됐고, 그런 부분들을 담당해 주는 게 아까 좀 전에 설명드린 것처럼 이제 인터넷망이라든지 뭐 대표적으로 우리가 쓰는 LTE나 5G망이 되겠죠. 이런 식의 통신 네트워크를 통해서 그 위성에 해당되는 내용들을 실제 아까 웨비나에서도 나왔습니다만은 기준국의 네트워크라고 표현을 하고 있었어요. 이런 식의 네트워크를 통해서 데이터를 전달해주는 어떤 릴레이에 대한 개념으로 접근을 할 수 있으면 충분히 해결이 가능한 어떤 우회할 수 있는 내용이 아닐까, 이제 이렇게 또 접근을 하고 있다, 이런 식으로 말씀을 드릴 수 있을 것 같고요. 일단 제가 흥미롭게 봤던 질문은 이 정도가 될 것 같습니다. 김영수 매니저님, 혹시 또 다른 어떤 질문 내용들 답변 주실 수 있을까요?
전 이제 흥미롭게 어떤 질문이라기보다는 이게 몇몇 질문들을 이렇게 보게 되면은 GNSS 약간의 오해가 있으신 것 같아서 GNSS라고 하는 거는 GPS의 다른 시스템이 아닙니다. 근데 지금 몇몇 질문들을 보면 아예 다른 시스템으로 생각을 하셔서 말씀을 드리면은 GNSS라고 하는 거는 글로벌 내비게이션 세틀라이트 시스템의 약자로서 그 위성을 가지고 항법을 하는 이 시스템 전체를 아우러서 지칭하는 총괄 말이라고 단어라고 생각을 하시면 돼요. 그래서 GNSS 안에는 뭐 미국의 GPS 북미 쪽에, 그다음에 뭐 러시아의 뭐 글로나스, 유럽의 뭐 갈릴레오 등등 다양한 이런 그 스탠다드들이 있는 거고요. GPS가 어떻게 보면 GNSS 안에 한 범주 안에 들어가 있는 용어라고 이제 혼동을 안 하셨으면 좋겠습니다.
아, 그러면 우리가 흔히 GPS라고 부르는 부분은 정확히 말하면 그 미국에서 배포한 위성 시스템의 이름. 예, 흔히 우리는 GNSS, 이 내비게이션 시스템 자체를 GPS와 동일시하고
그쵸,
있는
예.
부분이 좀 있는데 사실 이게 엄밀하게 따지면 GNSS 안에 포함되는 개념이다라고
그렇죠.
생각하는.
약간 GPS가 GNSS의 대명사 같은 느낌으로 많이들
그렇죠.
이제 사용을 하고
알겠습니다.
계시죠. 그리고 또 이렇게 보시다 보면은 뭐 대들 리코킹 같은 기술은 GNSS 솔루션 자체가 아니라 제가 이야기 바라는 후처리 기술을 이용하는 그 기술이었는데 당연히 뭐 연동을 할 수 있는 솔루션은 있을 거라고 생각이 되고요. 그다음에 좀 보다 보면은 뭐 이제 GNSS 이제 고정을 GNSS를 이용해가지고 뭐 다양한 이제 그 항법뿐만 아니라 다양한 어플리케이션으로 사용할 수 있는 내용들이 있는데요. 지금 임재철 님이 말씀해 주신 이런 내용들이 하나의 그런 분야라고 보시면 될 것 같아요. 그래서 그 GNSS 수신기를 가진 어떤 차량이 있다고 하면은 저희가 지금 하이패스를 이용해서 통행료를 지불하는 게 하이패스 카드를 이용해서 통행료를 지불하는 게 아니라 위치를 기준으로 해서 그 하이패스를 지나갈 때 통행료를 계산할 수 있는 그런 시스템들이라고 보시면 될 것 같고요. 아직 국내에서는 활용 분야가 인프라가 어떻게 됐는지까지는 파악이 되지가 않아서 그 부분은 뭐 나중에 저희가 확인이 되면은 말씀을 드릴 수 있도록 하겠습니다. 이것도 보면은 뭐 이런 질문들이 좀 종종 있었는데 간섭이 심한 위치를 지날 경우 어떻게 위치 측정을 큰 오차 오류 없이 유지할 수 있을지 궁금하네요. 오늘 세미나 중간중간에 저 부분에 대해서 저거를 어떻게 오차를 보정하는지에 대해서 내용들이 나오긴 했는데 다시 한번 이제 말씀을 드리면은 멀티패스나 이런 간섭에 의한 경우는 뭐 그 듀얼 밴드 두 가지 주파수를 쓰거나 여러 가지 스탠다드 GPS 갈릴레오 글로나스의 스탠다드를 쓰거나 거기에 나아가서 보정 정보를 받는 고정밀 GPS니 RTK나 PPP RTK를 사용해서 그런 거를 이제 그 위치를 오차 오류 없이 유지할 수 있는 이런 솔루션이라고 보시면 될 것 같습니다. 그래서 시간이 더 많은 질문을 하게.
네, 그 시간이 지금 약간 오버됐어요. 그래서 지금 5시에 저희가 끝나는 시간이었는데 지금 5시 2분이 됐습니다만은 저는 요거 하나 정도 더 답변해 주셔도 괜찮지 않을까 싶습니다. 여기 최상혁님 이제 영어로 적어주셔서 맞는지 모르겠습니다만은 여기 지금 보시면 그 30초 이내 위치 산출 시간 이런 얘기들을 지금 물어봐 주셨는데 혹시 이 부분 어떻게 간단하게 답변이 가능하실까요?
지금 질문하시는 내용은 테스트 관련된 부분이 이제 먼저 들어오신 것 같고요. 당연히 그 수초 안에 들어올 수 있게끔 저희는 테스트 솔루션을 제공을 하고요. 저게 아마 위출 시간이 30초라고 말씀하시는 거는 아까 전에 GMV에서 말한 그쪽 내용에서 나왔던 30초를 의미하시는
내비게이션
것
어플리케이션.
예, 내비게이션
예.
어플리케이션을 말씀하는 것 같아서 저희 쪽에서 테스트 부분은 당연히 수초 이내로 음영지역이 있을 때 들어올 수 있는 시뮬레이터를 제공을 하고 있다고 보시면 될 것 같습니다.
네, 왜냐하면 저희 쪽에서 저희가 로데 슈바르즈에서 제공을 하고 있는 솔루션은 테스트를 위한 위성 시뮬레이터라고 생각하시면 가장 간단할 것 같아요. 위성은 사실 24시간 뭐 보통 영어로 이제 보통 24/7이라고 표현을 합니다만 연중 무휴로 신호를 계속 쏘고 있는 거기 때문에 측정 장비에서는 어떤 지연 시간이나 이런 게 없이 원하실 때 언제든 바로 신호를 생성해서 제공을 할 수가 있게 될 것 같고요. 이 신호에서 얼마만큼 빠르게 위치를 산출할 거냐, 이건 이제 어플리케이션이 어떻게 구현되어 있느냐, 이런 문제로 서로 좀 분리가 될 필요가
네,
있다,
맞습니다.
이런 얘기를 해주신 것 같습니다.
약간의 오해는 좀 있으신 것 같으시네요.
이게 사실 뭐 개념상으로 또 오늘 말씀드린 내용들이 또 좀 그 내용상으로 좀 방대한 부분도 있었기 때문에 좀 그런 부분에서 좀 섞일 수 있는 내용이 아니었었나 생각이 들기도 합니다.
네네.
예, 저희 지금 5시 거의 5분 돼가고 있습니다. 오늘도 시간이 약간 더 좀 더 길어졌는데요. 예, 오늘 뭐 저희 준비한 웨비나 내용이 또 여러분들께 또 도움이 됐기를 바랍니다. 오늘 말씀드린 내용들에 대해서 또 더 자세한 내용이나 혹은 어떤 솔루션에 대한 측정 솔루션을 말씀드립니다만은 솔루션에 대한 어떤 자세한 정보가 필요하신 분들께서는 저희 로데 슈바르즈 코리아 쪽의 내용을 문의해 주실 수 있습니다. 그래서 아마 저희 쪽 이메일 주소라든지 좀 세일즈 코리아 골뱅이 로데슈바르즈.com 뭐 이런 식으로 저희 쪽 대표 이메일 주소를 저희가 제공을 하고 있습니다. 그래서 이런 부분들 참조하셔서 필요하신 부분들 언제든 저희 쪽으로 연락 주시면 좋을 것 같고요. 참고로 말씀드리면 오늘 내용에 대한 발표 자료와 동영상은 저희 로데 슈바르즈 코리아 홈페이지를 통해서 여러분께 제공을 해드릴 예정입니다. 물론 다시 보기는 톡아이티에서도 가능할 거고요. 그래서 이런 부분들 참조해 주시면 후에도 여러분들께서 필요하실 때 이 내용들 다시 한번 보실 수 있지 않을까 생각이 됩니다. 네, 오늘 저희 준비한 내용은 여기까지입니다. 그래서 오늘 웨비나 다시 한번 여러분들께 참석해 주신 여러분들께 감사드리고요. 저희는 이 정도로 오늘 정리하도록 하겠습니다. 다음에 또 더 재미있는, 더 흥미로운 내용들로 또 다시 여러분들 찾아뵙도록 하겠습니다. 감사합니다.